But so here's what we see today, is that the universe, the density of the universe is about 73% vacuum, or this stuff called dark energy. We don't know exactly what it is, but it is well described by an energy associated with empty space. About 23% is dark matter. We also don't know what this is, but we know it behaves differently than dark energy. This dilutes with expansion like matter and not like vacuum or radiation. We know that much. And then about 4% of the universe is all the stuff we know about, everything on the periodic table, the atoms, mostly hydrogen and helium, with trace elements of the rest of the stuff, right? So in fact, we've only actually managed to identify about 4% of the contents of the universe. Everything else we only know about indirectly from their gravitational influence on the things that we can see. So I guess this is job security. There's a lot of work left to be done, right? So that we've only identified 4% of the universe. The other 96%, we really don't know what it is. We just know it's out there because of the way it affects the things we can see. So how do we constrain this with observation? Right? We're doing science here. This is not philosophy. We want to actually use data to constrain these models and to constrain these properties of the universe. And the way we do that is we use time machines. In particular, time machines like this thing, which is the James Webb Space Telescope. Right? Telescopes are time machines because the speed of light is finite. When we look out in space, we're also looking back in time. In fact, the speed of light is not all that fast. Light goes about a foot per nanosecond. So in the time it takes your cell phone to do one computation, light travels about 30 centimeters or about a foot. And that means that on cosmic scales, this is glacially slow. It takes light 8 minutes to get from the sun to us, so that when we look at the sun, we're seeing it as it was 8 minutes ago, not as it is now. When we look at the center of the galaxy, we're seeing it as it was 30,000 years ago because it's 30,000 light years away. It takes light that long to get to us. When we look at the Andromeda galaxy, we're seeing it as it was 2.5 million years ago. If we look at a galaxy a billion light years away, we're seeing it as it was a billion years ago. So cosmologists are lucky, unlike archaeologists who have to reconstruct the past from bones and relics and leftover clues. Cosmologists can actually just look out and see the entire history of the universe stretched out in front of us in the light that is coming to us from more and more distant objects. So this is one of the deepest images of the universe that's ever been taken. This is a recent picture by the James Webb Space Telescope. And what you're seeing here is mostly galaxies. These are some foreground stars here, but all these smudges here are galaxies in the distant universe. And you really should think of this as not just a picture of the universe today, but it's actually a timeline showing you the entire history of the universe back to when it was only a few 100 million years old. The most distant objects in this photograph are almost all the way back to the Big Bang. So the light was emitted from them when the universe was only a couple of 100 million years old. And you see in objects just stacked up at different redshifts, right, at different amounts of light, different amounts of travel time, you see the whole history of the universe spread out, the history of formation of galaxies, all of these things, you can just see them in a single photograph. So the most distant object that has been found by the James Webb Space Telescope so far, and this is a very recent result, is this guy right here, which is at a redshift of 13.2. That means that the light from it has been stretched in wavelength by a factor of 13.2. So all the photons that would have been emitted in optical wavelengths are now in the infrared. That's why the James Webb Telescope observes in the infrared, because otherwise you wouldn't see these distant objects because the light is stretched so much by cosmic expansion. And this corresponds to a look-back time of about 13.6 billion years. So that little red smudge, you're actually seeing it as it was 13.6 billion years ago. The universe is only 13.8 billion years old. So this was a galaxy that you're seeing when the universe was only about 200 million years old. And in fact, this is so far back, it's causing problems for our standard dark matter-based models of structure formation, is that there shouldn't be big galaxies that early in the universe. And so this is sort of a bit of a puzzle, because we didn't expect to see large, well-formed halos that far back at about 200 million years. So this is already starting to challenge our theories of structure formation and so on. Note that this does not mean the Big Bang didn't happen, as you might have seen in the press, right? This just means that our standard dark matter-based theory of structure formation needs some modification, but the Big Bang theory is holding up really well. This is exactly what you would expect Big Bang cosmology, is you're seeing these very old, very highly redshifted galaxies in these images from Webb. So we can just actually just look back out in space and look back in time, and we can see the whole history of the universe as it happened. We don't have to guess. It's not speculation. It's not just mathematical model fitting. You're actually observing that entire history. So here's a remarkable picture. This is a map of galaxies, right? This is by the Sloan Digital Sky Survey. So in this picture, this is 200,000 galaxies and quasars. So each dot in this picture is a galaxy like the Milky Way, with 100 billion or 200 billion stars in it. And this is the real distribution of actual galaxies in our universe. This is a real three-dimensional map. If you look, and it's wedge shaped, because if you look at a strip on the sky, so we're here, and if we observe a strip on the sky and then expand that depth out into distance away from us, then it looks like a wedge, right? So we're sitting here and we're looking out in the universe, and this is a look back time here of about, so this is a redshift of 5, which corresponds to a look back time of about 12 billion years as the most distant objects in this map. So we are now producing the first three-dimensional maps of the universe out to distances of look back times of about 12 billion years, a little bit more. And we're actually seeing how the galaxies and the structure in the universe evolves. We can directly observe all of this stuff and use it to fit our models and understand the processes that are going on in the universe. So you don't have to guess. It's not theory. You can just go out and observe it. So as we look out in space, we look back in time, right? But the universe has a finite age, right? So we have a look back time of 12 billion years. This thing is at a look back time of about 13.6 billion years, but the universe is only 13.8 billion years old. So if we look out, if we could build a telescope that looks far enough out in space, far enough back in time, we would see the Big Bang happen. And in fact, no matter what direction we look, if we look far enough back in time, because the Big Bang happened everywhere in an infinite space at once, we would see the Big Bang as it happened in that direction, right? This is the idea of a cosmic horizon. So imagine at the moment of the Big Bang, you have one observer who lets a flashbulb go off, or a supernova happens or something. He sends out a light pulse, right? That light will travel out from him at the speed of light, but because the universe has a finite age, and the age of the universe, it can travel a finite distance. It's not hard to imagine that that's also as far out as he can see. If this is, so the radius of this sphere of light he sends out is the speed of light times the age of the universe. So he can't see anything out of that circle. So despite the fact that the universe is infinite, we can only see a finite patch of it, because the universe has a finite age and light has a finite speed. Anything outside this circle, like this observer, the light from him hasn't had time to get to him yet, because the universe isn't old enough. So now as the universe expands, our observable universe, the little patch of it that we can see, expands outward from us at the speed of light. It gets bigger and bigger, so we see more and more and more of this universe as time goes along, and then eventually this guy can see this guy because the light from this guy has had time to reach him. And so we actually only ever see a finite part of the universe. So what we actually see when we're sitting in this infinitely large homogeneous space is we see ourselves at the center of a sphere, a spherical universe, and the edge of that sphere is the Big Bang itself. And if we look out from here all the way out, if we could see all the way out to the edge of this, what we would see is the Big Bang, and we would see it happening in every direction. So the Big Bang isn't a point out there in space, it's a sphere with us at the center. Now, we can't see all the way out to the Big Bang itself. I mean, one more point on this is an observer-dependent effect. It's like the horizon on Earth, right? If I stand here, I can only see out a certain distance because of the curvature of the Earth. Somebody else standing at a different spot will have his own horizon, and those may or may not overlap. So everybody sees them, and in cosmology, it's a similar thing. Everybody sees themselves at the center of their own observable universe, and those observable universes may or may not overlap. But it's an observer-dependent effect, just like the horizon is on Earth. Everybody sees the same thing. It still obeys the cosmological principle. Now, we can't see all the way back to the Big Bang, because very early on, the universe was so hot and dense that it was opaque. You want to think of it as like a big, thick fog that's scattering the light so rapidly that you can't see through it. This is the early universe, when the hydrogen and helium in the universe, the atoms, right? So the only elements that were produced in the Big Bang were hydrogen and helium. and everything heavier was produced later on in the cores of stars and supernovae and things like that. And so the very early universe where this hydrogen and helium would have been extremely hot, and it would have been so hot that it was ionized. The electrons were stripped away from the nuclei, and so you would have had this plasma, which means that you have the positively charged nuclei here. The electrons would have been freely roaming around in space, and the light scatters very strongly off those free electrons. And so this would have been a very hot, dense, glowing gas that you couldn't see basically your nose in front of your face because it's this thick fog that the photons are scattering rapidly. When the universe was about 400,000 years old, a little less, about 380,000, and the temperature of the universe dropped below a temperature of 3,000 Kelvin, these ionized atoms would have captured the electrons and gone from ionized to being electrically neutral, so that there was a transition that happened where all those once the gas got cool enough, these electrons would be captured by the nuclei. And then the universe at that instant, very rapidly, became transparent, and all this light that was trapped in this ionized plasma would be released and starts free streaming through space. The universe was transparent, and this light is still out there. Because the universe is expanding, it's gradually cooling. So at this time, it was 3,000 Kelvin. It would have been like a very hot oven. It would have been sort of a glowing red oven if you would have been able to see it with your eye, right? It would have been a very inhospitable place, but it would have been in the visible wavelengths. But the universe since then has expanded by a factor of about 1,100. And so these photons have increased in wavelength by about a factor of 1,100, and now they're in the microwave wavelengths. And this is the cosmic microwave background. So this is light that is directly left over from the Big Bang. And if we look back to a look-back time of just when the universe was only about 400,000 years old, we see this light coming to us from what's called the surface of last scattering. So this is now, these wedges here are the Sloan Digital Sky Survey. This is these maps of galaxies. Now this is showing the look-back time all the way out to 13.8 billion years. And as far out, but you can't see all the way back to the Big Bang. You can just see to this, what's called the surface of last scattering, the point where the universe went from becoming opaque to being opaque to becoming transparent. And the light you see is primarily in the microwave, and this is called the cosmic microwave background. So this is correct to scale. This is as far out as we've gotten our maps of the galaxies. These gaps in this map are because of the plane of the Milky Way that we can't see through our own galaxy well enough to measure the positions of other galaxies. But this is a remarkable picture because we're actually starting to map out significant fractions of our observable universe quantitatively. This is real data. This is the real positions of real galaxies again. And this image here is a real image of the cosmic microwave background. And so here is, so we are at the center of this sphere. This is the sphere of the sky looking out at this light left over from the Big Bang. So we don't see the Big Bang, we see this glowing sphere of light that is the light that was released when the universe became transparent at an age of about 400,000 years. And this is showing the Planck satellite image of the fluctuations in this. So this is the variations in the temperature of this primordial light, vastly exaggerated, right? So all these photons, all the light coming to us from the early universe is exactly the same temperature to 1 part in 100,000. And these little 1 part in 100,000 variations, the red things are hot spots, the blue things are cold spots, are caused by the primordial density fluctuations in the universe. These hot spots are a little denser than their neighbors, and these cold spots are a little less dense. These are the seeds that later collapse to form galaxies and structure in the universe. So you had these when the universe was 400,000 years old, you had these 1 part in 100,000 fluctuations in the density that created these variations in the temperature that you can map out with satellites now. So this is real observations of the light coming to us from the Big Bang. And then all of these little overdense regions would then collapse under gravity, and they were the things that form stars and galaxies and so on, right? So we can actually observe, this is a picture of a real picture of the universe when it was 400,000 years old. We're seeing the primordial seeds that formed all of the structure in the universe before any of that structure formation happened. We can observe it directly. So this is very powerful, and this has been a 30-year effort.